Assalamu alaikum students. Welcome to lecture 22 of data structures and algorithms. We are working with trees and we use chapter 13 of book 1. In the last lecture, we implemented code to determine if a binary tree is an ACBT. We were introduced to depth-first tree traversal algorithms. We implemented code for in-order traversal, and we examined all codes for time and space complexities. Breadth-first traversal. In this traversal, we first visit all the nodes in one level and then we move to the next level. Start at the root. Within the same level, visit nodes from left to right. When all nodes in level K have been visited, move to level K plus 1. We print the data field of a node when we visit it. This traversal is like reading English text on a page. You start from the top, you move from left to right in a line. Once a line is finished, you move to the next line. Let us do breadth first traversal of this tree. I start at the root, which is A, and as I get to a node, I print it. Then from A, I will move to the next level because level 0 is done. The next level is level 1 and I start in it from the left. So I come to B and I print it. Then I move towards the right. I go to C and I print it. Level 1 is complete. I move to level 2. The leftmost node in level 2 is D and I print it. I move towards the right. I come to E and I print it. Then I come to F and I print it. Level 2 is complete. Let's start level 3. The leftmost node in level 3 is H. I print it. Move towards the right. I go to G and I print it. Level 3 is complete. Level 4 has only one node. I go to I and I print it. This is the traversal sequence for breadth first traversal. Have a look at the code for breadth first traversal. We call it traverse BF, and this is one of the functions in the class B tree. When the function starts, we take a Python list called nodes and we put the pointer self in it. We are assuming that self is pointing to the root of a tree whose traversal we have to do. So after we put self in the nodes list, we print the data field of self. Now we initialize two variables. I is going to keep track of the index of the current element and n is going to keep the total number of elements in nodes. While I is less than n, move into the while, take a node from the nodes list. Here we are taking the ith element. This is our P or parent. Now see if this node P has a left child. If it has a left child, we print the data of the left child and then we add the left child of this node in the nodes list. And since we have added an element to the nodes list, we increment n. Then we check if P has a right child. If so, we print the data of the right child and then we add the right child to the end of the nodes list. Since we have added an element to the nodes list, we increment n. Now that we have done everything with nodes I, it's time to move forward, so we increment I. At the end of the traversal, we simply print an empty line. Let us look at the time complexity of this function. The while loop iterates as many times as the number of nodes in the tree. The body of the while takes O1 time. So the time complexity of traverse BF is On. What about space complexity? Two integers I and n, a B-tree object P, and a Python list nodes is used by the traverse BF function. The list nodes contains as many elements as the number of nodes when the loop completes, so its maximum size is n. From this we can conclude that the space complexity of traverse BF is On. Building a binary tree. This code uses functions of the class btree to create a binary tree for the val list. This is an input Python list which contains values that you want to place in the binary tree. If you want to create empty slots, they can be represented by none. When the function starts, it checks if the length of val is 0 or if the first element in val is none. If any of these conditions is correct, it returns none or no tree at all. But if both these conditions are false, then it takes the 0th element from val, calls the init function of btree, makes a new btree node, puts val 0 in it, and this becomes our root. Now the root node is placed in another Python list called nodes. We have two Python lists now. One is val, which is the input list. One is nodes, which is what we are making as we are creating nodes. We have two variables keeping track. One is n, which keeps track of item in nodes. The other is I, which keeps track of item in val. We have just added val 0 to the tree. That is why I starts from 1. We are going to add nodes to the root, which is the 0th element of nodes. So n starts with 0. While I is less than len-val, take the nth element of nodes. This is our P or parent. Now look at the ith value of val. If it is not none, then make a left child for P and place val I in it. Now that you have created a new node, append this node in the nodes list. You have done whatever was necessary for the ith value of val. So increment I. Again check if the ith value of val is not none. If it is present, then create a right child for P and place in it the ith value of val. Then append this new node to the nodes list. Since we've done all the necessary work for the ith value of val, we need to increment I. And in the end, since this node in the nodes list has been given both a left child and a right child, we should move to the next node, so n is also incremented. At the end of the while loop, we return the root. Some homework. The Python list val is shown to you. Run the build tree function to build a tree from this input. Draw the tree and determine the time and space complexities of the build tree function. Searching in a binary tree. This function returns a list of two elements. Recall that I told you that mostly people search because they want to delete next. And in the tree structure, if you want to delete a node, you require the pointer to its parent. That is why our returned value will mostly be not the node which contains target, but parent of the node which contains target. We give the search function two arguments, the root node and the target. Four different conditions of the base case can happen. The first condition is that whatever node is given to me is not a B tree node, or it is none. Then I will return none 0. This means that no node exists. If target is present in the node that is given to me, I return node 1. 1 signifies that this node itself contains the target. The third case is when target is not present in the node given to me, but it is present in the left child of the node given to me. Then I return node 2. 2 signifies that the target is present in the left child of the node that I am returning. See, I am returning not pointer to the node but pointer to the parent. The last condition would be when target is not present in the node given to me but in the right child of the node given to me. Then I return node 3. 3 signifies that target is in the right child. If none of these conditions are met, then I call the search function within itself. So this is recursion. And I pass to it this node's left child. Actually, I am asking the search function to restart the search in the left subtree of this node. This search function will return to me a list of two elements. I call it x. Now, if the 0th element of x is none, this means that target was not found in the left subtree. But if the 0th element of x is not none, this means that the target has been found. And so I do not search the right subtree, I return x. But if x0 is none, this means the target has not been found. So I call the search function recursively for the right subtree of the node given to me. And whatever is the return value from this function is my final return value. Run the search function on the tree shown here for targets B, F and J. Explain what the return lists contain for each of the targets. 2. What is the worst case of the search function? 3. Determine the time and space complexity of the worst case. Now we are going to talk about a kind of binary tree called a heap. A heap is an almost complete binary tree in which the nodes are organized based on their values. There are two variants of the heap structure. A max heap has the property known as the heap order property that dictates that each non-leaf node contains a value greater than the values in its children. The largest value is stored in the root. For the min heap, the heap order property dictates that each non-leaf node contains a value smaller than the values in its children. The smallest value is stored in the root. Max heap. In the remainder of this discussion, we will be concerned with max heaps only. So whenever I talk of heap, I am talking of the max heap. This is a heap. How to convince yourself? Start at the root. The value of the root is greater than the value of its children. Come to 84. The value is greater than its children. Come to 71. Again the value is greater than its children. Look at node containing 60. Its value is greater than both its children. The node containing 23 has only one child. However, the value at this node is greater than the value at its only child. So this proves that this is a heap. Storage of an ACBT in memory. The heap is an ACBT. There are no gaps in between nodes of an ACBT. The Python list or an array can be used to store a heap. We place the root at index 0 of the list. If the parent is at index I, the left child is placed at index 2i plus 1 and the right child at 2i plus 2. If a node is at index j, its parent can be retrieved from j minus 1 whole divided by 2 and we take the floor value of this expression. Now we are asked to store the heap shown here in a list. We start at the root and we place the root at index 0. In the Python list, it appears like this. Now, the node containing 100 has a left child containing 84 and a right child containing 71. 100 is placed at 0, so I is 0. 84 will be placed at 2i plus 1, 2 into 0 plus 1 or 1. 71 will be placed at 2i plus 2, 2 into 0 plus 2 or 2. And this will appear in the Python list like this. Now, the node containing 84 is at 1, so its left child should be at 2 into 1 plus 1 or 3. 60 should be at 3. Its right child should be at 2 into 1 plus 2 or 4. 23 should be at 4. Look at the node containing 71. It is at 2. 12 should be at 2 into 2 plus 1, 5. 29 should be at 2 into 2 plus 2 or 6. So these are the indexes that we calculated for these elements, and this is how they appear in the Python list. 60 is at 3. Its left child should be at 2 into 3 plus 1 or 7. 1 should be at 7. And its right child should be at 2 into 3 plus 2 or 8. 37 should be at 8. 4 is the left child of 23. 23 is at 4. So 4 should be at 2 into 4 plus 1 or 9. These are the indexes that we have calculated for the last level nodes, and this is how they appear. And we have finally stored our heap in a simple Python list. Finding the parent. First we are asked to find the parent of 37. 37 is at 8. So j is 8. J minus 1 whole divided by 2. 8 minus 1 7 divided by 2 3.5. Now take the floor of this value, toss the 0.5 away. You are left with 3. At 3 we have 60. So this means the parent of 37 is 60. Now we are asked to find the parent of 12. 12 is at 5. J is 5. 5 minus 1 is 4. Whole divided by 2 is 2. The floor will also be 2. At 2 we have 71. So this means the parent of 12 is 71. This is the node. This is the parent. Are we correct? Let's look at the original figure. The parent of 37 is 60 and the parent of 12 is indeed 71. So this way we can not only store a heap in a Python list, we can retrieve parent or children of a node within the Python list. Adding to a heap. Append the new element to the end of the list so that the ACBT is preserved. Make the new element rise to restore heap order property. So what do you mean by rising? Repeat as long as node's value is greater than parent's value or you do not reach the root. Swap values of the node and its parent. I have a heap over here. You can see that 33 has children which are lesser than it. 24 has children which are lesser than it. 11 has children which are lesser than it. And 12 has one child which is less than it. I want to add 30. I am going to add 30 as the very last node. To the Python list, it will be appended as the last element because I do not want to do anything wrong to the ACBT that I have. I want to preserve it. So this is 30 and it is added to 12. Now the ACBT is as it was, but this is not a heap anymore because it is violating the heap order property. See, 12 has two children and one of them has a higher value. So this means that 30 is not at its correct position and it will have to rise to its correct position. I look at 12 and 30 and I swap the values. After the swap, 30 and 12 are at their correct position. Now I consider 30 and its new parent, 24. Again, this is not in line with the heap order property. So I am going to swap the value of 30 and 24. In other words, I am going to make 30 rise. Now this is the correct way for 30 and 24 to be in a max heap. Now I am going to compare 30 and its new parent, 30 and 33. But this is okay. So I say that 30 has risen to its correct position and 30 has been added to the heap. Analysis of the rise function. The worst case happens when a node must rise all the way to the root. Height of a perfect binary tree of n nodes is log whole n plus 1. Height of an ACBT of n nodes is O log n because the number of nodes in ACBT is less than or equal to the number of nodes in a PBT. In the worst case, the maximum number of swaps is log n. The rise function uses a temporary variable to help in swapping. From this we can conclude that time complexity of the rise function is O log n and space complexity of the rise function is O1. Building a heap. Repeat as long as there are elements. Add this element to the heap as described earlier. Now you are asked to build a heap from the given list of values. I take the first value, 34. I make it the root of my tree. I start a Python list and I append 34 to it. So the Python list currently has only 34. Now I take the next value and I am going to add the next value to the tree that I have. So I add 56. You see it added in the tree. In the Python list, it has been appended. Now I see whether 56 is at its correct position or it needs to rise. It needs to rise. See that 56 and 34 have been swapped. This is okay now. The next element is 29, which will be appended to the list. In the tree, it will appear like this. Now I will see whether 29 is at its correct position. Yes, it is. Let it be. The next element is 45. See whether it is at its correct position. No. Make it rise. Now, check with its new parent. Is it at its correct position? Yes, it has risen to the correct position. Let it be. The next element is 37. See whether it needs to rise. No, let it be. The next element is 68. See whether it needs to rise. Yes, swap the values of the parent and the child. Now check the value of the new parent and 68. Does it need to rise? Yes, swap. Now the heap is okay. We have built a heap from the input Python list. See that our heap is also contained in a Python list. Your homework. The Python list val is defined thus: 5813 69274. Build a heap from this input. Show how this heap is stored in memory. What is the time and space complexity of building a heap? Deleting from a heap. Always delete the root. Make the last element the new root so that the ACBT is preserved. Make the new root sync to restore heap order property. So what is syncing? Repeat as long as the node's value is less than value of any of its children or you do not reach a leaf. Determine the child with the greater value x and swap values of the node and x. Deleting from a heap. The first thing that we are going to do is we are going to delete the root. So we delete 33. This does not remain an ACBT. To preserve the ACBT, we take the very last node and make it the root. So 12 is taken and placed at the root. But this disturbs the heap order property. Consider this triangle, the parent 12 and its children. Is the value of the parent larger than both its children? No. Now locate the child with the higher value, that is 30. So we sync the root towards the greater child. We are going to swap 12 and 30. Now 12 is the parent of 24 and 3. Again see if 12 is at its correct position. No, it has a child with a greater value. Locate the child which has a greater value in both children. 24 is greater than 3. So we will sync 12 towards the greater child and we will swap 12 and 24. This is done. Now consider this triangle. 12 has only one child now. Does the child have a lesser value? Yes. So 12 has sunk to its correct position. Let it be. What did we just do? We deleted the root and restored the heap back to a max heap. Analysis of the sync function. The worst case happens when a node must sync all the way to a leaf. Height of a PBT of n nodes is log of n plus 1. Height of an ACBT of n nodes is O log n. In the worst case, the maximum number of swaps is log n. The sync function uses a temporary variable to help in swapping. From this we can deduce that the time taken is O log n and the space taken is O1. In this lecture, we were introduced to breadth-first tree traversal algorithm. We were introduced to the heap. We learned how to add to, build, and delete from a heap. And we examined all codes for time and space complexity. So now I will ask you to read the book, do the homework, note your questions and your suggestions, and either put these up in the online session or write me an email. Take care of yourself. Allah Hafiz.